Here are the answers for the section 4-10 homework, beginning on page 150. Use the factor theorem to determine if the linear binomial is a factor of the polynomial. So in number 1, here is our linear binomial. This fits the form x minus a. It's called linear because the variable x goes to the first power. So in our binomial, the value of a is the number 7. A is 7. Here is the polynomial that we want to know if x minus 7 is a factor. Does x minus 7 divide evenly into the polynomial with a remainder of 0? The factor theorem gives us a technique to use to find out. With the factor theorem, we take the value of a, which in our case is 7, and substitute it in place of the variable x. When we then evaluate the polynomial, if we get an answer of 0, then we know that x minus 7 is a factor. So let's substitute in 7 and then find out what we get. 7 squared is 49. 49 take away 35 is 14. And 14 plus 14 is 28. We did not get a 0, so we found out that x minus 7 is not a factor. Next, number 3. Does this 4-term polynomial divide evenly by x minus 3? Because this is a linear binomial factor, we can use the factor theorem. In this case, the value of a is the number 3. So substitute a 3 where all the x's are and evaluate this polynomial. So 2 times 3 cubed minus 11 times 3 squared plus 12 times 3 plus 9. We need to know what this is equal to. 3 to the third power is 27, and 2 times 27 is 54. 3 to the second power is 9, and 11 times 9 is 99. 12 times 3 is 36, and on the end plus 9. Now let's combine these 4 numbers together. These add up to 0. Because we get a 0 when substituting a 3, that tells us that x minus 3 is a factor. Number 9, show that x plus 2 is a linear factor of this 4-term polynomial. And after we show that it is a factor, find the other linear factors. If x plus 2 is a factor, then it will divide into this evenly with a remainder of 0. Let's use long division and see what we have after we divide it. Inside here, put the 2x cubed minus x squared minus 7x plus 6. Now focus on leading terms, on the x and the 2x cubed. X times 2x squared makes 2x cubed. And the 2x squared times 2 makes positive 4x squared. Now subtract. Negative 1x squared subtract 4x squared is negative 5x squared. Bring down the negative 7x. Now focus on leading terms again, on the x and the negative 5x squared. X times negative 5x is negative 5x squared. And negative 5x times 2 is negative 10x. Now subtract. Negative 7x subtract negative 10x is 3x. And bring down that plus 6. X times what makes 3x? We need a positive 3. 3 times x is 3x, and 3 times 2 is positive 6. Notice when you subtract, you do get 0. That tells us that x plus 2 is a factor of the polynomial. What we have just figured out is that our polynomial can factor into x plus 2 times 2x squared minus 5x plus 3. Now we can factor this trinomial using FOIL. So we have our x plus 2, and then 2 sets of parentheses. 2x times x is the 2x squared. What times what is positive 3? And notice that the middle is negative, so we need a negative number times a negative number to make positive 3. It's going to be a 3 and a 1, but it matters where we put them. Let's put the 3 here and the 1 here. so that the outer product is negative 2x and the inner product is negative 3x. Those combine to the negative 5x. So here is our factored form using all linear factors. Number 11, let's show that x minus 1 is a factor of this. If it is a factor, it will divide in there with no remainder. Let's use long division to divide it into that polynomial. X times 2x squared makes 2x cubed. And 2x squared times negative 1 is negative 2x squared. Now subtract. 1x squared subtract negative 2x squared is 3x squared. And bring down the negative 5x. X times positive 3x makes 3x squared. And 3x times negative 1 is negative 3x. Now subtract. Negative 5x subtract negative 3x is negative 2x. Bring down the plus 2. X times negative 2 is negative 2x. And negative 2 times negative 1 is a positive 2. And when you subtract, we do get a remainder of 0. So far we have factored the original polynomial into x minus 1 times 2x squared plus 3x minus 2. Now let's factor that trinomial using FOIL. So here's our x minus 1, and here's two sets of parentheses. 2x times x is the 2x squared. Now how can we get negative 2? We would have to have a positive and a negative, and we have to have a 2 and a 1. Let's put the 1 here and the 2 here. And put the negative here and the positive here. The reason I did that is so that the outer product makes 4x and the inner product makes negative 1x. Those combine to 3x. And that's what I was trying to make. So here is the factored form of the original polynomial. In number 13, we're asked to factor this polynomial. We found out in those last two problems that if we can find that first linear factor, that we can then factor the rest of it using our traditional factoring rules. So the trick is to find a linear factor. Let's use the factor theorem to help us. Simply guess what the linear factor might be. Maybe it is x minus 1. That would mean that the value of a is a 1. Let's substitute 1 where the x is and see if we get an answer of 0. If this does not make 0, we're going to try a different linear factor. 6 times 1 is 6, minus 7 times 1 is 7, minus 7 plus 6. This makes negative 2. So we found out that x minus 1 is not a factor. Let's simply guess another possible factor of the original polynomial. Maybe it divides evenly by x minus 2, in which case the value of a is a 2. Let's substitute a 2 in place of x and see what happens. Two to the third power is 8, and 6 times 8 is 48. 2 squared is 4, and 7 times 4 is 28. 7 times 2 is a 14, and then the plus 6. 48 subtract 28 is 20, 20 subtract 14 is 6, and 6 plus 6 makes 12. This did not make 0. We can try x minus 3, but we're not having very good luck trying linear factors that go x minus. Maybe x plus 1 divides evenly into the polynomial. I'm going to erase the work that we've done so far since it did not work and try x plus 1 as a linear factor. In this case, the value of a is negative 1 because x plus 1 is equivalent to x minus negative 1. Let's substitute negative 1 and see what happens. Negative 1 cubed is negative 1, and 6 times negative 1 is negative 6. Negative 1 squared is 1, and 7 times 1 is a 7. Negative 7 times negative 1 is positive 7, and on the end, plus 6. This is looking a lot better. The negative 6 and the plus 6 cancel. The negative 7 and the plus 7 cancel. This makes 0. This is very helpful because now we know that x plus 1 is a factor. We can use long division to find out what the other factor is. X times 6x squared makes 6x cubed. And 6x squared times 1 is positive 6x squared. Negative 7x squared subtract 6x squared is negative 13x squared. Bring down the negative 7x. X times negative 13x makes negative 13x squared. And negative 13x times 1 is negative 13x. Now subtract. Negative 7x subtract negative 13x is 6x. And bring down the plus 6. X times a positive 6 makes 6x. And 6 times 1 makes plus 6. We got a remainder of 0, which is good, or else we mess something up. What we just found out is that our original 4-term polynomial can be factored as x plus 1 times 6x squared minus 13x plus 6. Now let's see if this trinomial factors farther using FOIL. If it does factor farther, it will be 2 sets of parentheses. What times what is 6x squared? There are different possibilities. One of them is 3x times 2x. If we find out this doesn't work, we'll erase it and try 6x times 1x. Now the last number is positive, but the middle is negative, so these both have to be negative. Now there's different ways to make positive 6. It could be 1 times 6 or 2 times 3. Let's try the 2 and the 3. I'm going to put the 2 here and the 3 here. The outer product is negative 9x, and the inner product is negative 4x, and these combine to negative 13x. That is the middle term. So here in the box is our completely factored form. We used the factor theorem to help us discover that first factor. Then we used long division to find out the other polynomial that gets multiplied to that factor. Then we were able to use regular factoring to factor that trinomial. Number 15, let's use a similar approach, but we see that our original polynomial is even larger with a higher degree. Let's use the factor theorem to get us a linear factor. Maybe it's x minus 1. If it is, then the value of a is 1. Let's see what happens when we substitute in a 1. We're hoping to get lucky and that this works on our first try. 1 to the 4th is 1. 1 to the 3rd is 1, and 16 times 1 is a 16. 1 squared is 1, and 86 times 1 is a positive 86. 176 times 1 is a 176, and on the end, plus 105. Let's take a calculator and add all this up and see what it makes. It makes 0, which is excellent, because now we know that x minus 1 is a factor. Let's use long division to figure out what polynomial is multiplied to the x minus 1. Oops, as I started writing this, I noticed I keep speaking about x minus 1, but in number 15 it's the letter y. I wonder why I didn't discover that earlier. This is actually y minus 1, and the thing that we were testing up here was y minus 1. I get so used to using x, but of course we don't always use x. So inside the bracket we have y to the 4th power minus 16y cubed plus 86y squared minus 176y plus 105. Let's do our long division. Y times y cubed is y to the 4th. Y cubed times negative 1 is negative 1 y cubed. Now subtract. Negative 16 Subtract negative 1 is negative 15y cubed. Bring down the positive 86y squared. Y times negative 15y squared is the negative 15y cubed. And negative 15y squared times negative 1 is positive 15y squared. Now subtract. We get 71y squared. Bring down the negative 176y. Y times positive 71y makes 71y squared. And 71y times negative 1 is negative 71y. Now subtract. We get negative 105y. And bring down the positive 105. Y times negative 105 makes negative 105y. And negative 105 times negative 1 makes positive 105. When you subtract, we do get a remainder of 0, as we expected. So right now, we've written it as y minus 1 times y cubed minus 15y squared plus 71y minus 105. Does this four-term polynomial factor farther? Well, it probably does, but we need to find a factor that will work. Let's use the factor theorem again. What would you like to try? Do you think y minus 1 might be a factor again? If so, then the value of a would be 1. Let's see what happens when we replace the letter y with a 1. We would have 1 cubed minus 15 times 1 squared plus 71 times 1 minus 105. Does this make 0? Let's take a calculator and find out. No, this turns out to be negative 48. Y minus 1 is not a factor again. Let's erase this and try another factor. Because the constant term ends in 5, it might be worth trying y minus 5. If we do, then the value of a is a 5. Let's just see what happens when we substitute 5 in place of y. Let's take a calculator and type this all in and see if we get a 0. And you know what? It does make 0. So y minus 5 is a factor of our original polynomial. Now we can use long division to figure out what gets multiplied to the y minus 5. So y minus 5 divides into, with long division, y cubed minus 15y squared plus 71y minus 105. Y times y squared makes the y cubed. And y squared times negative 5 is negative 5y squared. Now subtract. We get negative 10y squared. And bring down the positive 71y. Y times negative 10y makes negative 10y squared. And negative 10y times negative 5 makes positive 50y. Now subtract. We get 21y. And bring down that negative 105. Y times positive 21 makes 21y. And 21 times negative 5 makes negative 105. And when we subtract, we do get 0 as we expected, because we already knew from the factor theorem that y minus 5 would divide in evenly. I'm sort of running out of room, so let me scroll this down a little bit, and we're going to write out the factored form that we know so far. The first factor we discovered was y minus 1. The next linear factor we just discovered was y minus 5. And the remaining factor is y squared minus 10y plus 21. Does that trinomial factor more? Let's try FOIL on it. Two sets of parentheses. We can go y minus 7 times y minus 3. Here is the factored form of our original polynomial. So that was a really long question because it was a 4th degree polynomial, and it took us some guess and check to find those initial factors with the factor theorem. For the review assignment, we're going to page 147 where we were dividing polynomials. In number 2, we're dividing this trinomial by a monomial. When you divide by a monomial, the fastest way is the distributive property. 21a to the 4th divided by 7a minus 14a to the 3rd divided by 7a plus 7a squared divided by 7a. Notice we're dividing every term of the top by the bottom. Now let's simplify. This is 3a cubed minus 2a squared plus a. For number 4, we're also dividing by a monomial, so let's use that same technique. 36a to the 4th divided by negative 6a squared plus 18 a cubed b divided by the negative 6a squared minus the 24 a squared b squared divided by the negative 6a squared. Now simplify each term. 36 divided by negative 6 is negative 6. A to the 4th divided by a squared is a squared when you subtract the exponents. Positive 18 divided by negative 6 is negative 3. A cubed divided by a squared is a single a, and there is a b on the top. Now the last term, negative 24 divided by negative 6 is positive 4. A squared divided by a squared cancels away totally, and there's a b squared left in the top. So here's the answer. Number 6 has that same pattern. Take each term of the numerator and divide by that denominator. Now simplify the terms. Be careful with the negative signs and be careful you're using the subtracting exponents rule correctly. A positive divided by a negative is negative. R squared divided by a single r leaves a single r. The s's cancel out. Now in the middle, negative divided by negative is positive. R squared divided by a single r leaves an r. S squared divided by a single s leaves an s. Now the last term, negative divided by negative is positive. There's a 5. The r's cancel away, and s squared divided by s leaves an s. Here's the answer. Number 12 is also division, but we're dividing by a binomial. So the distributive property is not going to be the best way. Instead, let's use long division. We happen to have done that already in this assignment. So we're going to take our 2a minus b and divide it into the trinomial. 2a times 6a makes 12a squared. And 6a times negative b makes negative 6ab. Now subtract. Negative 4 subtract negative 6 makes 2ab. And bring down the negative b squared term. 2a times a positive b makes 2ab. And b times negative b makes negative b squared. When you subtract, it makes 0. So our answer is above the bracket. Number 18, we can use the same technique. Let's divide the x minus 3 into the trinomial. X times x is that x squared, and x times negative 3 is negative 3x. Now subtract. 1x subtract negative 3 is 4x. And bring down the negative 8. X times positive 4 is that 4x. And 4 times negative 3 is negative 12. Now subtract. Negative 8 subtract negative 12 makes 4. And that's called the remainder. We add that remainder onto the end of our answer and use the x minus 3 as a denominator. So here's the answer to the question. Next, page 146. Here's where we were graphing inequalities. The technique was to get a 0 on the right and factor the left. This factors into d times d squared minus 25. But d squared minus 25 is a difference of squares, and it factors into d plus 5 times d minus 5. Now we're going to think of all the cases where we could have three things times together and get an answer greater than 0, which means positive. One possibility is that all three of them are positive. So d is greater than 0, and d plus 5 is greater than 0, and d minus 5 is greater than 0. But another way for three numbers to multiply together and end up greater than 0 is if two of them are negative and one of them is positive. So maybe the d is the one that's positive, and the d plus 5 is less than 0, and the d minus 5 is less than 0. Now case number 3. Maybe the d is less than 0, and the d plus 5 is less than 0, and the d minus 5 is greater than 0. Or case number 4. Maybe the d is less than 0, and the d plus 5 is greater than 0, and the d minus 5 is less than 0. A negative times a positive times a negative does make a positive answer. Let's go back for every one of these cases and solve for d. This one here is good to go, but in the middle we could subtract 5 from both sides, getting d is greater than negative 5. Right here we could add 5, getting d is greater than positive 5. D is a number that's more than 0, it's more than negative 5, and it's more than positive 5. We could write this with a single expression, d is greater than 5. Look at case 2. This one's good to go. This one here we could subtract 5 from both sides, and this one we could add 5 to both sides. We want d to be greater than 0, and at the same time less than negative 5. That's not possible. This is empty set. Now case 3. This is good, but right here in the middle we need to subtract 5 from both sides. And over here, add 5 to both sides. D is a number that's less than 0, and it's less than negative 5, and it's greater than positive 5. Now, you can't be less than negative 5 and be greater than positive 5. This is an empty set. Okay, now the last one. This one's okay. Right here, we need to subtract 5 from both sides, and here we need to add 5 to both sides. D is a number. It's less than 0. And it's greater than negative 5, and it's less than 5. That's possible. We could write negative 5 is less than d, which is less than 0. This satisfies all three of these descriptions. So for our graph, we want to show this part and show this part. So if this is positive 5, we can put an open dot and shade to the right. That takes care of case number 1. Now case number 2, here's 0, here's negative 5. Put an open dot on these and shade in between. That takes care of case 4. Number 18, we don't have a 0 on the right side, so let's create a 0 by subtracting 81 from both sides. We get 0 is greater than or equal to s to the 4th minus 81. But we still don't have the 0 on the right side. Let's switch the sides using the symmetric property. We have s to the 4th minus 81 is less than or equal to 0. Notice when you switch the sides, the arrow has to switch as well. Let's factor this. This is a difference of squares. S squared plus 9 times s squared minus 9. S squared plus 9 is a sum of squares. We have no special pattern for that. But s squared minus 9 is another difference of squares. It will factor more. We can use s plus 3 times s minus 3. And that's less than or equal to 0. Now let's consider cases. We have three things, and we want the result to end up less than 0, which means negative. For three numbers to multiply together and end up as a negative, there have to be an odd number of negatives. So case number 1, maybe they're all negative. the s squared plus 9 is less than or equal to 0, and the s plus 3 is less than or equal to 0, and the s minus 3 is less than or equal to 0. Case 2. It's another way that three things could multiply together and end up less than 0. Maybe one of them is negative and two of them are positive. So the s squared plus 9 might be less than or equal to 0, and the s plus 3 greater than or equal to 0, and the s minus 3 greater than or equal to 0. Now case 3. Maybe the s squared plus 9 is greater than or equal to 0, and the s plus 3 is the one that's negative. Or case number 4. Maybe it is the last one that's negative. So the s squared plus 9 is positive, and the s plus 3 is positive, and that last one is the one that's negative. Positive times a negative would make an answer that's less than or equal to 0. Let's go to case 1 and solve these pieces. This first piece is interesting. Let's think about what happens here. Remember that s squared can never be negative. If this can't be negative, then when you add 9 to it, you cannot get an answer less than or equal to 0. Case number 1 is going to result in an empty set because of this first piece. We don't even need to look at these two. Case number 2 has that same situation, and so it's an empty set. Now case number 3, what numbers could you use for s so that when you square them and add 9, you get an answer greater than or equal to 0? Any number at all is going to work for this. So this does not create a problem for us. Let's take a look at these two and work out what s is. This one makes s is less than or equal to negative 3. And this one makes s is greater than or equal to positive 3. What kind of numbers are less than negative 3 and at the same time greater than 3? There aren't any. This is an empty set. Now case 4. We were just discussing this. This is not a problem. Any number at all will work for s. Let's look at these two pieces. This makes s is greater than or equal to negative 3. This one over here makes s is less than or equal to positive 3. Let's put these two statements together. It's telling us that s comes between those two numbers. And this is something we can graph. So we have negative 3 and positive 3, closed dots on both of them, and the shading in between. Page 129 goes way back to when we were just multiplying things together. We have a binomial, we want to times by a trinomial. We're going to do the distributive property twice. Let's start with the x and multiply it to all three of those terms. X times x squared is x cubed. X times y squared is positive xy squared. X times negative xy is negative x squared y. Now go to the y and distribute it to all three of those terms. Y times x squared is positive x squared y. Y times y squared is positive y cubed. Y times negative xy is negative xy squared. Let's see if there's any like terms. We have a positive xy squared and later a negative xy squared. Those will cancel each other away. We have a negative x squared y and later a positive x squared y. Those will cancel each other away. It looks like we're left with x cubed plus y cubed. That's a sum of cubes. I bet if we had been paying close attention earlier and considered rewriting it so that the negative xy came in between those two, we may have recognized that that was the factored form of a sum of cubes. And we could have got directly to this answer without doing out the distributive property. Now number 30, we have a bunch of binomials. Let's use the distributive property again more than once. Focus on just this section here and times those together with FOIL. We're going to have our 2n minus 3 out at the beginning, and then we're going to get a trinomial when we do FOIL. n times 3n is 3n squared. N times negative 2 is negative 2n. 1 times 3n is positive 3n, and these combine to positive n. And 1 times negative 2 is negative 2. That's called the distributive property, or more commonly, FOIL. Now we've created the same situation we just had in the previous one. Let's do the distributive property twice. Start with the 2n and times it to all three of those. 2n times 3n squared is 6n cubed. 2n times n is positive 2n squared. And 2n times negative 2 is negative 4n. Now jump over here to this minus 3 and distribute it to all three of those. Negative 3 times 3n squared is negative 9n squared. Negative 3 times n is negative 3n. Negative 3 times negative 2 is positive 6. Let's look for combining like terms. We've got our 6n cubed at the beginning. It's our highest degree term. Now look at the n squareds. 2n squared minus 9n squared. It's negative 7n squared. Now look at the n terms. Negative 4n and negative 3n. That's negative 7n. And our constant is the plus 6. Then, page 129, let's square this binomial. The fast way to square a binomial is to square the first term. We get z to the 6th. To double the product of the two terms, when you times these together, it's negative 3z cubed. When you double that, you get negative 6z cubed. And then square the last term. A negative 3 squared is a positive 9. If you don't remember the fast way to square a binomial, you can always write it out twice and then use FOIL to times them, but you will get that same answer.